just an alpha.
It is.
Just.
All right. Should I start? Should I wait a little longer? Looks like there's still some people.
Can you stand a little closer this way? You're just like not.
Ah, okay. Wait, where is the camera?
You're good. I don't know.
I'll just start. Okay, so I'm presenting some preliminary results so these are building on some previous works that were using the LLC to detect developmental stages in language models. So some of these results are like extremely hot off the press, as in like just finished literally yesterday, which, like that wasn't stressful at all.
You're interpreting them in real time.
Yeah, so this work will hopefully be on archive soon. It's not yet, but please keep an eye out. So we did this work at Timaeus. These are the co-authors on this work, which I think everybody is. Oh, Zach's not here, but everybody else is in the audience. Yeah, this is going to be a little bit light on technical details. So the main point of this talk is just to showcase that there are like nice applications of the learning coefficient and some recent progress on expanding it. So a quick outline. I'm going to start with the talking a little bit about the LLC and some previous work that we've done, or previous work that this is building off of and some work that we've done. I'll go over the methodology that we use in this work, then introduce this new thing that we're calling refined LLC, and then I'll go over two main examples to sort of walk through some the methodology of using the refined LLC. One of them is an induction circuit, which has been previously studied in small transform models, and then one is a sort of new structure that we're thinking of as a trigram circuit. And then I'll end with some discussion and some teasers of future work. Okay, so the global learning coefficient, it's a quantity, it measures model complexity. You've probably seen this like a dozen times during this conference already, so I won't spend too much time on this. Informally, we can just think of this as starting from some model checkpoint. You perturb the model parameters and then take the average loss and run this through some equation in order to compute the LLC, or estimate it rather. So this is like the actual equations for this, which again, I won't go into too much detail, but basically we have like some posterior, we have some sampling process, we sample from this posterior, take the average loss, and then plug it into this equation, and boom, LLC. Okay, so how do you use this? So from Zach's talk, so he points out that although we can accurately estimate the LLC in cases where we have access to the ground truth, we often don't have access to the ground truth. And so in those cases, we can't really be sure that we're accurately, precisely measuring the true LLC. We can, however, tune our hyperparameter selection so that we can be sure that certain things that we can use in cases where we don't have the ground truth are still preserved. So one of those is, for example, relative ordering, which is to say that if you have one LLC that is, say, larger than another one, that this is sort of preserved under whatever the true relationship of LLCs is. And we also want to have some confidence that if the LLC that you're estimating is rising or falling, then this corresponds with real rises and falls in the true LLC. Okay, so this leads us to this particular methodology, which is that you train a model, you save a bunch of checkpoints, you have this sort of training trajectory of the model. You do this step with calibrating hyperparameters. I'm going to carefully sweep that under the rug for this talk. But if you want to learn more about what happens at this step, there's a lot that I can say about this, and I'm going to lead a session on this on Monday afternoon. And then you run your LLC estimates over training, you get this curve of LLC estimates, and then you look for critical points on this curve. Intuitively, we might think of this as something indicating that the model is sort of saturating on some internal structure or behavior or learned information or something like that. And then finally, since our work is largely about validating that this works at all, we look at some other metrics in order to check that these critical points actually do correspond with sort of meaningful boundaries of developmental stages. And I'll also add that these other methods that we use to check are meant to be things that are more established, more straightforward metrics. Things like looking at attention scores or ablations or things like that. And so we sometimes get asked if you can sort of like validate that these stages exist or discover these stages using these other methods, why bother with the LLC at all? So I guess to that I would say that there's something quite powerful about having a general technique that just sort of works without needing to know anything a priori. And you can learn really meaningful things about the model or the training process by doing this general thing that doesn't require like sitting down and crafting bespoke metrics about whatever the thing is that you're trying to understand. So a limitation of that, of course, is that for the LLC, this means that even though you can measure that something meaningful is happening, you do at some point still need to go and check what the meaningful thing that's happening is. So it is still a bit blind in that sense, but some of the work that we'll present today sort of makes some progress towards closing that gap. Okay, and then why do we care about this? Well, so broadly, developmental interpretability is motivated by DevBio. And so the basic shape of the argument is something like you can get a lot of useful information about an organism by understanding how it develops. So things that we might learn in the case of frontier AI, we might learn things like how models learn patterns, where models learn patterns, and that in turn might mean that we can learn things about specific capabilities that we care about. And then eventually, maybe someday, we can sort of steer these models towards safer things or away from more dangerous things. So to draw on Jesse's metaphor in his opening talk, in the metaphor of alchemy, we're trying to understand something about how the sort of reaction process in the cauldron actually happens. And without understanding something about how you throw things into the pot and then get alchemical outputs out the other side, we can't really progress to chemistry. All right, so this work originally builds on some work that Anthropic did studying small attention-only transformer models. So they looked at 3 different types of models, 0-layer models, 1-layer models, and 2-layer models. So the 0-layer models are not technically transformer models, they're just embedding and unembedding layer. But in this case, they are able to learn bigrams, which is just 2 token sequences in the model, or sorry, in language. 1-layer models are able to start learning skip-trigrams, which is this sequence where you sort of have a bigram thing, but you also look back to a token earlier in the context, and this helps you better predict the next token. And then by the time you get to 2-layer models, you can start getting some sort of interesting interactions between heads. In this, the example here is that you develop this thing called an induction circuit. And so here, induction is this pattern of, you have this like earlier sequence in a context, and then it repeats itself maybe once or twice or more times later in the context. And you can look back from later instances to earlier instances and then use this to better predict the later instances. And so this is particularly useful when you're considering things like names or things like chemical compounds or other kinds of like rare sequences that would be weird to memorize. So the sort of example that Anthropic gives is this excerpt from Harry Potter, where it shows that the model is sort of like at some point in training, you get this like phase transition where the model is able to suddenly start performing better on the name Dursley in this excerpt. Okay, so we looked at this, we saw phase transition, and we were like, hey, we bet SLT and DevInterp can say something interesting here. So earlier this year, we used our methodology that I previously mentioned to explore small transformer models trained on a language task and also on a linear regression task. So I guess the linear regression task is also quite rich, and I think Liam will be talking a little bit about some downstream work from that tomorrow. But since this talk is mostly about language modeling, I'm going to focus on the results from that. So you might have seen this plot in a couple of talks already, but basically here at the top is the training loss that you see for the for a 2-layer attention-only transformer model. And then here is the sort of computed LLC estimate over the course of training. And then according to the methodology that we're using, we just look at these sort of like flat regions in the LLC curve. We put lines down on each of these, and then we sort of claim that these are the developmental stages of the model.
Okay, can I ask something about on in the last stage of the fluctuation, is it just an artifact of the compression or is it something?
Let's see. I would say that it is something.
Because it's on the log scale, right? So maybe.
Yeah.
Or
So
just that complex?
I think this basically. I'm not going to go over like results related to this. I think in this talk, but through other experiments, I think there is actually sort of something meaningful happening around that stage, but it's like the actual location is a bit like fuzzy because it is like log scale compressed. But there is like reason to suspect that is like sort of a real boundary.
I think that wasn't quite the question. There's high variance in the LLC estimate in the final stage.
Yeah. Oh, this.
Yeah.
Oh, yeah. That's because of compression. Okay. Yeah. Sorry. Okay. So So in this work, we do in fact confirm that two-layer tension-only transformers acquire induction heads. And more than that, we show that the developmental stages that the model goes through actually parallel the capabilities obtained by increasing depth, which is pretty interesting on its own. So in this first stage, we see that the model is learning bigrams, and one way that we measure this is through measuring the bigram entropy, cross entropy against bigram statistics. And so what we do here is we just like literally directly count the number of bigram occurrences in the data. We accumulate those into statistics and then measure the cross entropy of the model's outputs against the like whatever would be predicted by just naively predicting bigram statistics. And then we see that at the end of the first stage of training, the model sort of comes closest to emulating these bigram predictions before moving on to other things. And then like over here, for example, we have some stuff indicating that around the third and fourth stage, the model is learning to do in-context learning. So here, this is the ICL score, which is difference in loss between tokens later in context and tokens earlier in context. And so an improvement on this suggests that the model is getting better at predictions later in context, and therefore should be using information from earlier in the context as part of its predictions. And then here are just like some sample metrics for attention scores for previous token heads and induction heads, which are the constituent parts of the induction circuit, and we see that these have a rise in these stages. Yeah.
Oh, it was just a really elementary. So model score means it's doing better at predicting bigrams. It's doing worse.
Oh, so sorry.
Bigram score is?
Yeah. So the score here is a cross entropy against the bigram statistics.
Okay.
So the lower the score is, the closer it is to bigram statistics.
Right. Good. Okay. That's closer it is to just doing bigram statistics.
Yeah.
But not a measure of how good it does against bigrams. So that as it's going up, it's learning to do other things, but it would be still just as good at bigrams. Would it not?
So I guess it would be like if you were just predicting like the bigrams and there was no other information, then I guess you would hope that the model would like be equally good at this. Yeah. But then this goes up because predicting bigram statistics gets like relatively worse.
Right. Yeah. Thank you.
Okay, so what is this refined LLC? So here's the new thing. Informally, we can kind of think of this as just freezing some of the weights when we do this perturbation, and maybe computing loss using a different data set. And so the idea here is that you can, so where the LLC tells you something about how the model as a whole changes over the course of training with respect to the pre-training data set, the idea here is that you can understand something about arbitrary components of the model, which are the unfrozen weights, with respect to some arbitrary data set over the course of training. And then so here's like some math. Basically, you just restrict the posterior that you sample to the subset of weights that you care about, and then you like replace the loss with the loss on the different data set. Otherwise, everything's the same. And if the weights that are considered are the same as the original model, or the data set that you consider is the same as the pre-training data set, then you suppress the notation or refer to it as just the weight-refined LLC or data-refined LLC respectively. And then if both the weights and the data are the originals, then you just recover the original LLC and just call it that.
So I think it's data-refined or weight-refined respectively.
What?
Your the order in your respectively was it?
Oh, okay, sorry.
There are two questions.
Yes.
So is it correct that you don't necessarily fix some parameters, but you fix a direction in parameter space, or?
Yeah, so Yeah, so one way to think about it is just that you, like, in the original LLC, you perturbed like all of the model weights using like some like gradient process, and then in the refined LLCs for like some subset of the weights, you just project that sampling process down onto the
Okay.
the
Yeah.
subset.
I guess following up on that question, is it like maybe like are you only considering like basis aligned restrictions? Because like you could also like restrict to other linear projection subspaces. Or
Yeah, I think for now at least we're just considering basis. Okay. Any other questions? Yeah.
I guess what kind of data sets are you using as these modified data sets? Because if it's not like a subset, or at least like from a distribution that's similar to that of a subset of the pre-trained data sets, it's pretty unclear what, like how meaningful this quantity would be.
Yeah. So there's two things that we'll use in this talk. The first one is a data set from GitHub, which I think isn't strictly a subset of the original data set, but like the original data set I think does have code in it. And then the other is, I'll get to it. But yeah, I think it is probably, there's still like some work to be done on like this doesn't, yeah, you're right, like this doesn't necessarily just like a priori work on like, you could come up with like weird data sets or something where it might be hard to
General
work
thing
with.
is out taking sub-distributions of the training distributions.
Yeah. Okay, and then some other like miscellaneous notation and stuff. Throughout this talk, I might refer to specific attention heads. So a head in layer L with head index H is referred to as the head L:H, and both indices for those are starting at 0. Composition scores, these are these things that Anthropic studied. Informally, these are just like how much an attention head in one layer reads from the subspace that an attention head in another layer writes to in the residual stream. And then this is sort of like a measure of how much two attention heads compose with each other. And then frequently throughout this talk, we want to refer to both n-grams and skip-trigrams as like a whole. And so we'll just use the word trigram as a shorthand instead of repeatedly saying n-grams and skip-trigrams.
Do you have a question?
Okay. So we basically just repeat the same methodology as before, except we use these refined LLCs. So we have a model, we train it, we do a variety of weight refinements or data refinements, and then we look at the curves. But now, so in this case, we're looking at refinements over specific attention heads. So in these cases, all of the model weights are frozen except for a single attention head. And then in this case, we're doing the same weight refinement, except that we substitute the pre-training data set with a GitHub data set. Yeah.
sorry. For the attention head, are you considering like QKV and O, or just like which weights?
All of them.
Okay.
All right, so the title of this talk is about differentiation and specialization of these attention heads. So let me point out what we can see from just sort of staring at the curves. So let's first look at these weight-refined LLCs focused on, computed over the pre-training data. And we'll just like sort of look at them and see if we can do any sort of visual differentiation. So the first thing that we might look at is like, okay, these orange curves look kind of different. So they've got this kind of like pattern where they have two peaks here and they sort of like stand out compared to all of the other curves. And I guess like spoiler alert, these are the previous token heads. And so sort of just looking at the RLLCs, we can already distinguish that these heads are doing something different from the others. We have this other head, this red one is the head 05. We're not going to talk about this one too much in this talk, but this is sort of like off doing its own thing. And then you have these other heads in layer 1 that all sort of share the same shape, which is this sort of like rise and then a peak and then a second peak and then fall.
Sorry, George, can you
Yes.
give us a sense of how large the model is, the
Yeah. Yeah, it's a attention only 2-layer transformer. The total parameter count is about 3 million. And then I think besides that, the other like difference is that so this is the same model that we trained for the Hoogland et al. Work. And just to keep like the model size smaller, we originally trained it with a tokenizer size 5,000 instead of 50,000. Yeah.
So you have said before that I should really take the y-axis here very seriously. I guess if it were the case that there's sort of a constant factor between this y-axis and the correct y-axis that's the same over all t, then I could just go, well, I know roughly from elsewhere what the LLC is at initialization, and I know roughly what I maybe expect to be a date of training, and I can read off what sort of the true absolute scores are. But that only works if the scale, doesn't shift over training. Do you think it shifts or it doesn't shift?
I don't know. Yeah, I think this is something that we haven't investigated very much.
There's some reason to think that it might, for instance, given that you get like negative LLCs at the beginning of the first epoch or two of training, so like it kind of has to shift or something at the very beginning.
Yeah. That doesn't sound very promising.
Yeah.
So what's the
Final question.
Like, I really would like to have like actual correct, in the scale correct LLC values to work with here, and this would tell me a lot of how to take these results. And if it were the case that the only way that this y-axis absolute is off is that I have to multiply it by some factor, but the factor is the same factor for the entire plot, and it would be fine. I can make some educated guess about what the LLC at the status, I don't know what the end it might be, and then I know what everything else is. But if the scale by which this sampler sort of off shifts over training, then yeah, I can do that.
Yeah, I think that's a good question, but I think we just don't know right now.
Why are heads 1 and 4 different?
Oh, these are the previous tokens.
Those are the previous. Okay.
Yeah, okay, so then we have this like 0, 5 head, we have these double bump heads in layer 0, and then over here we have kind of like maybe 2 visual clusters of heads. So one is this one where it sort of like rises steadily and then they all share this peak at the same time. And then you have these 2 down here, which again, I guess like spoiler, these are the induction heads. So I guess just looking at this, we can already like have some like differentiation power between these heads, which I think is pretty significant. I will note that a priori, the induction head curves here don't look the same, so you actually can't we know from elsewhere that these are both induction heads, but from this graph you might not guess that they're doing the same thing. But then actually, another sort of like spoiler for later in the talk is that they aren't quite doing the exact same thing, and this is something interesting that you can differentiate from these curves as well. Okay. So here are the same weight refinements, but this time we're using the GitHub dataset instead of the pile dataset. So from here we were previously looking at these 2 graphs, and now we're looking at these 2. Okay, so sorry, let me go back one more time. So looking at the full model LLCs, there's already like kind of something interesting happening here. So here you can see that there's like a flat region here that distinguishes these 2 stages. But in this case, it kind of like smooths out into, like you can't really like distinguish the early stages anymore. But then there is a really sort of like noticeable increase in the stage where it starts learning to do induction. And we think this makes sense. So the early stages are in some sense about memorizing common sort of like 2-token or 3-token or 4-token sequences in the data or something. Whereas in this stage, like those tokens that you memorize in the earlier stages might not be very useful for code, where you have a lot of sort of like syntactical tokens, you have a lot of like unique repeated variables. But those are kind of the, like unique repeated variables are kind of exactly the kind of thing that you would expect induction to be good at helping you predict. And then we see one other interesting thing, which is that if you look at the induction heads here, these two brown curves, they're very clearly sort of like at the bottom of the RLLC values for layer 1. But if you go to the GitHub refined LLCs, instead of being at the bottom, they jump to the top. And so remember I said earlier that one of the things that we care about is trying to have some process where we can sort of trust the relative ordering of LLC values. And so here, we would sort of expect or hope that this indicates something about these heads being particularly specialized or interested in code style text. And then one last interesting thing here is that in this graph, both of the induction heads kind of end at around the same point in terms of RLLC value. Whereas here, the head 1.6 actually ends sort of noticeably higher than 1.7. And so if all of the things that we're sort of like hoping for are true, then we might, for example, hope that, or predict that this means that 1.6 is somehow more specialized for code than 1.7 is.
Why is there a divot?
Oh, this?
Yeah, and like all the plots.
Yeah, I think this is some artifact. There's like some noise in the estimation process. It's probably just an artifact of that.
Would all the noise be correlated?
Oh, this is I think because
The noise is correlated between SQL and runs.
yeah, because we're using seeded runs.
Okay. Oh yeah, I guess they.
Well, these scores go down at the end.
So we have some speculation about this. So we kind of like don't know in general why, like, so reasons why LLC like goes up or down are both kind of like a bit speculative. Some ideas that we have for things causing LLC to go down are things like I guess it's something that we're calling like algorithmic crystallization, which is something like once like a structure is developed, then maybe like the structure can become like more polished or more crystallized or like made more solid somehow, and this might correspond to LLC going down because then it's like more resistant to perturbation or something like that. There's some other hypotheses that we have, like maybe this is related to like redundancy. So like if you have two attention heads that do the same thing, then perturbing one of them might not cause like a loss to be impacted as much because the other sort of like picks up the slack, so to speak. And if you don't have redundancy, then this might not be the case. But yeah, I think it's a good question. I think it's still
Thank you.
Okay, so so this is literally just from looking at these curves. What do we learn? So one is that we have these visual clustering of attention heads. So this might let us differentiate between different types of attention heads in the model. And we ended up with these 5 different clusters down here. And then we also get some insight into how these heads are specializing. So we can distinguish the attention heads from the other heads just by like sort of visual inspection. But then we also get to see sort of like what they're better at. And then even between the two attention heads, we might be able to see something about how these are specializing relative to each other. So it remains to be seen whether these takeaways are real or not. So let's start getting into some of the other metrics to show whether these interpretations are actually correct. Okay, so in these plots, I guess we're basically trying to check whether there are other structural metrics that coincide with these critical points. So one thing that we might look at, for example, is this composition score, where we look at how much the induction heads are composing with the previous token heads in order to form this circuit. And if we look at these red and orange lines in these plots, these are the composition scores of head 1.6 with both of the previous token heads, and these are the ones for 1.7 with both of the previous token heads. And then we can see here there's a sort of plateau in the composition score that coincides with the second peak here. And then this isn't quite a peak, but there is sort of a clear kink in the curve here where that corresponds with the plateau in the composition scores in that case as well. And then if we look at the previous token heads and their RLLC curves, then we see that there's sort of like a first peak here that coincides with the plateaued composition score, and then same for the second peak in them. And then I guess as like a sort of sanity check, we would hope that if you have sort of weight-refined LLCs on one data set and weight-refined LLCs on another data set, they should try to give you like some sort of like correlated information, and we can look and see that sort of the peak of the two attention heads in the refined LLCs on the pre-training data coincide with the peak for the GitHub data. Okay, so these are all good signs. Let's see if we can also figure out why one of these attention heads seems to respond more to the GitHub data. And so, again, recall that we saw that 1.6 ends at a much higher RLLC than 1.7 does. And if we look at what they're doing, so on this slide we have a few samples of mean ablations. So in these examples, the blue token indicates the next token being predicted. Orange indicates attention score. So these are truncated examples, so all of the attention is like much earlier in the context. So if you look at head 1.7, for example, this looks like very much like the type of attention head, like induction examples that Anthropic had. So these are like names. You have like some chemical compound or like medical, like medicine. And then if you look at 1.6 instead, you see like a pretty substantially different pattern where rather than sort of focusing on words, you see this like sort of like syntax. And in the second example, I guess you can already see that there's like this previous instance of this token sequence. But like on the third example, for example, this came from some sample where there were a lot of like dates and then at and then some like location of an event or something. Okay, so if 1.6 really is like an attention head, or an induction head that's like sort of more about syntax or special characters, then this basically gives like a pretty natural hypothesis for why it's more important for code, or why it like responds more to code, which is that code has a lot of syntax and special characters. And yeah.
Is there intuition on, I forgot which one it has higher and lower LLC. Is there intuition just looking at this that
1.6 has higher LLC on the code,
Yeah.
right?
higher LLC on the code,
Yeah.
but
In general, it has
In
the
general,
same.
it's the same.
okay, right, it ends at the same.
Yeah.
They have a different trajectory, like in the middle stages that I don't particularly understand.
Yeah, that's right. Okay, so yeah.
Have you tried looking at whether they have the same specialization over time as well?
We haven't looked at them over time.
Okay.
Okay. Okay, so what do we learn from looking at this example? So the first is just that if you look at the weight-refined LLCs, you do in fact get to sort of distinguish the induction heads away from the other heads in their layer. We already knew that that was the case. We just from like previous research, we knew that these heads were the induction heads. But we also know from the GitHub data RLLCs that these induction heads are actually distinct from each other. We actually see that from the difference in curves from the regular weight-refined LLCs. And then the GitHub LLCs show us how they're distinct from each other. And these are both things that we didn't know a priori from previous research. Okay. All right, so before I go on to the other sort of main example for this talk, I'll introduce this notion of a baseline. So these are models that are separately trained in order to capture some specific behavior. So this L0 baseline is a zero-layer transformer model, and the L1 baseline is a one-layer transformer model, and these are both trained on language prediction. And the idea is just that since we know that zero-layer transformers learn to predict bigrams and one-layer transformers learn to predict trigrams, then respectively these are sort of baseline models that capture the behavior of bigram or trigram prediction. And so we can run samples through both our model and the baseline model, and then look at the model outputs and run the cross entropy against those. And in some sense, this should tell us how much our model is emulating this behavior of bigram or trigram prediction, respectively. In the bigram case, we can also check that this sort of corresponds with the empirical bigram cross entropy. And here they might look a little bit different because the x-axis is off. But they do both minimize at the end of the first stage. And then here the L1 baseline suggests that the model is sort of closest to predicting trigram statistics at the end of the stage where we expect them to be done learning trigram statistics. Yes?
Sorry, can we go back?
Yes.
These are sorry, these are loss curves, not LS curves.
Yeah, these are loss curves.
Oh, sorry.
Yeah.
My question.
Yeah, I guess the point of this is just to be like, okay, yeah, these actually are meaningfully capturing some behavior that we want them to be capturing.
Right, thanks.
Okay. Okay, so this is the other main example, which is something that we're calling the trigram circuit. So on these 4 plots up here, I'm partitioning the attention heads in the model. On the left side are the layer 0 attention heads, on the right side are the layer 1 attention heads. Up here are these curves that are the attention heads that have these like double peak curves. So it's the same as these ones here. And those are the blue lines. And then down here are the previous token heads and the 0, 5 head. On the left side, or sorry, on the right side, we have the layer 1 attention heads. Down here are the 2 induction heads, and here are the rest of the layer 1 heads. And then what is the green line? Well, this is rather than computing the refined LLCs on some other data set, you can actually replace some other data set with the baseline and put in the cross entropy against the baseline outputs as the loss function, and then get a refined LLC with respect to some baseline. And that's what these green lines are plotting. So in some sense, when we are trying to compute these refined LLCs with respect to the L1 baseline, we are kind of trying to measure something about where the structure in the model is that's like responsible for simulating that behavior or something. So if you have like some part of the model that is like sort of particularly strong on the like baseline refined LLC, then this suggests maybe that part of the model is responsible for doing that behavior. Okay, so looking at the top plots, I want to make some sort of claim that if you eyeball these curves, that the layer 1 heads up here sort of change relatively less than the other clusters of attention heads. And so if there is some structure in the model that is...
change mean like the blue and green curves
like,
yeah.
Yeah, okay. And then rather than sort of just asking you to trust me on this, here are some, an attempt to sort of quantify this. So here we have, so these blue lines are taking the difference of the blue and green lines at the top and then dividing by the blue line. So this is just measuring a % drop that the green line has relative to the blue line. And then the black dotted line is just a reference point to show that, in fact, the curves up here, as a function of like % difference, do change less relative to the other curves. Yeah.
Can you re-explain what's the difference with the baseline? Are you just like running the LLC estimate on a different data set with the same model, or?
Yeah. So this is, you're running the LLC estimate. You're using the pile, like the pre-training data, but then you run the baseline on the sample to get logic outputs, and then you take your model and take the cross entropy of your model against the baseline models.
Oh, so it's changing like the loss function you're using in the estimator.
Yeah, yeah.
So what are the 2 layers again? So there's the first row and the second row. How are you splitting up the attention heads again?
So this is just basically just by like visual shape.
Okay, cool.
Yeah, so this is, these are both layer 0 heads, these are both
Yep.
layer 1 heads, and then this is some of the layer 0 heads, some of the layer 0 heads. Any other questions?
I have a general question. So how much should we trust these visual eyeballing? Like say I see something that looks like it has 2 peaks. Should I think of it as, oh, this could be an induction head, or should I be like,
Something that I wanted to ask about this, I mean, that doesn't the logarithmic scale actually make the effect less impressive than it would be? I mean, if you plot plotted this thing on a linear scale, that would, because this logarithm tends to compress actually the curves and make them maybe less visually different than they would be.
I agree that they look visually different. I think that, not really sure how to answer.
I guess the problem is
this first question. Yeah, George is making a subset of the statements that to you might look reasonable based on the picture, and like he didn't say anything about the double bumps, like meaning something necessarily. That's because we sort of know that this particular feature of the curve is not like universal across 4 choices of hyperparameters or whatever. So there's like behind what George is saying, like a sort of a sense that some of the features of the curve seem more robust than others, and this is like a developing story. So I think, if I understand correctly, George is probably like restricting what he's saying to the subset of the things we see in the curves that seem to be like both pretty robust in terms of the way we're producing these numbers, and we can sort of argue for. But yeah, you shouldn't necessarily go and look at these curves and get too excited about every feature of them at the current state of the techniques.
Yeah, I think that's right. Also, so it's like possible, for example, that you could have a curve that had 2 bumps in it, but then still like sort of looked really different. I know like sort of like looking at it is like not really like a rigorous like scientific technique or something, but I think, yeah, so I think probably as we continue to develop this technique, we'll also come up with like sort of better, like more quantifiable methods of
sorry.
No, that's, yeah. Oh yeah, okay, so there was one more thing that I was going to point out, which is if you, I guess, like believe that the locations of critical points should tell you like something meaningful is changing about developmental information, then we might also question whether something interesting is happening here, because we have this first peak of these curves that sort of coincides with this time when a shift in like learning trigrams and induction is happening.
So before we go on,
yeah.
Maybe you didn't give the punchline of this slide or something. So what does this say about where the information in the layer 1 baseline behavior is?
It's here.
It's in the layer 1 hits.
Yeah. Sorry. So, the idea is that if you have some cluster of heads where the refined LLCs are changing minimally relative to other heads, this should suggest to you that if structure exists for like sort of adhering to this behavior in the model, then it should exist in the place where the refined LLCs change the least.
And we sort of know independently this is a sensible answer, right? Like we look at these layer 1 heads and know they have to do with trigrams. Right?
Yeah.
Yeah. So this is like makes sense.
Yeah. Okay, so these are sort of like the 2 hypotheses that we walk away from just by looking at refined LLC curves. So the first is the one that I just said, and then the other is this idea that maybe because this has a peak that coincides with a specific time in development that we already know something about, maybe it has something to do with that development. Okay. same as with the induction heads, we're going to go through some of the other metrics that we looked at to validate our hypotheses. So there are two questions that we want to answer here. One is whether it's actually fair to call this a circuit, and if so, is this really a circuit about trigram prediction? So I won't be able to present, I guess, like all of the data that we have on this, but hopefully these are sort of the most convincing pieces. So one big thing that suggests that this is really some sort of structure is looking at composition scores. And so you can see that at this point in training, which coincides with like this peak here.
Sorry, I have a question. You're saying circuits rather than circuits. I gather that's intentional, probably because you can't clearly disentangle them, really. Is that right?
I think that's correct, yeah.
It's like all the layer 1 heads seem to depend on a lot of the layer 0 heads.
Right, yeah. So here you kind of see this like, so these plots show for a specific layer 0 head all of the composition scores with the layer 1 heads. And then when you, so the blue curves are the composition scores with the layer 1 heads that we sort of suspect are doing something about trigram prediction. And then we see this like really, not only is there like this noticeable change in K composition at this time, but there's like a very strong coupling between them, which suggests that so as Dan points out, that it suggests that there is like some like overlap and like interconnectedness between what's happening here. And so this is like a pretty reliable thing that happens for all of these layer 0 heads that we suspect are part of this trigram circuit.
What about the last one?
Oh yeah, this is the 0, 5 head that we were not gonna.
Can't do that to us.
Read the paper. Okay. Okay, so another thing that we can do is we can just look at ablation samples again. We are kind of thinking that these attention heads in layer 0 and layer 1, based on these like composition scores, probably have some sort of structure together. And so what is that structure? If we look at this slide, so sorry to jump around so much, but step 8.5K is sort of like this time in training where these like peaks are happening, and a little bit before, like, it's around the time where this like composition score kind of like turns around. So if this like sort of part of the development of these heads like indicates some shift, then like the point just before that shift should sort of tell us what they were doing before they went through this change. And so that's why we have the first row as being 8.5K and then 50K is the end of training. So if we look at sort of maximally impacted tokens on these samples, or for ablating these heads, then for one of the layer 0 heads that we look at that we think is part of this trigram circuit, is sort of independently responsible for predicting some trigrams. So like it is really likes the name Fitzgerald for some reason. It like predicts trigrams that start with like trans, and then like has like some other trigrams scattered around like envelope. And then at this early point in training, the head 1.5 is already kind of like pretty clearly doing this thing about like enclosing brackets. So here we have like enclosing brackets around shop committee. I guess I only did square brackets here, but I think it does like parentheses and like quotations as well. But then if we look at the end of training and we do the same experiment where we ablate a head and see what tokens get impacted the most, head 1.5 is still doing the same thing. So it's got like closing parentheses, closing brackets, but then 0.7 is no longer responsible for sort of predicting the trigrams that it used to be. Instead, you now see that ablating it seems to impact the same tokens that ablating 1.5 does. And so this like strongly suggests to us that whatever it's doing, it's like passing information forward to 1.5 in order to help it do its duties. Yeah, so then, yeah, from this and digging through some other like samples and metrics, we basically suppose that early in training, so like kind of like during this stage, the layer 0 heads and layer 1 heads are sort of independently responsible for predicting their own trigram patterns. And then once this happens, and these composition scores, once this happens and these composition scores turn around, then somehow these like layer 0 heads become subordinate to these layer 1 heads and mainly act to pass information forward in order to help them predict better. Okay, so what did we learn from this example? Well, first is that there's a trigram circuit at all, which was not known before, as far as we know. So it was previously known that these models could do trigram prediction, but the actual mechanism behind this wasn't previously studied. Just like with the induction circuit heads, we can just do visual clustering from the...
Sorry, but to be clear, of course everybody knew how to predict some trigrams, but you're talking about a particular class of things like nested brackets or whatever, which can't be done by a single layer.
Yes, but I think I also mean just the fact that there is this like circuit structure. Because like you could like just assume that the layers are independently.
Okay, yeah, trigrams. So
Yeah. So let's see. Yeah, so just like with the induction circuit heads, we can just by like sort of visual clustering, we can pick out the heads that are part of this trigram circuit just by looking at the weight refined LLCs. And then finally, we can use some version of data refined LLCs in order to give us insight into what type of specialization the structure is interested in. Okay, so then overall, what do we learn from these LLCs? First is that we do get meaningful developmental signals from these. These developmental signals allow us to differentiate model components, such as attention heads, into pieces of structure. So the differentiation that you get does successfully partition attention heads into sort of like actual structures in the model. And then you can even learn what those structures do by adjusting the data used to compute the RLLCs and looking at sort of the response of the curves. Okay, so restated another way, these LLCs, the original LLC tells you something about the development of the entire model in relation to the pre-training data set, but refined LLCs let you understand how the development of arbitrary components of the model relate to arbitrary data sets. This is a pretty powerful thing to be able to do, and in theory this should just work for arbitrary models and arbitrary data sets. Okay, so what kind of doors does this open? Well, before it can open many more doors, I think there's still quite a lot of future work on engineering and implementation improvements. So a big part of that is improving compute efficiency and improving hyperparameter selection. So recall that I swept this under the rug earlier, but this is very much not a trivial part of this work. And if you want to learn more, again, I'm giving a talk on Monday. Yeah, and then this also unlocks a lot of interesting applications. We want to, like, for example, work on scaling this up to larger models. So can we do things like automatic circuit detection for GPT-2 scale models? We're interested in looking at the intersection between SAEs and SLT. So for example, something that you might do is take SAEs trained on a model, pick out some features, filter data sets for samples that like activate particularly strongly on those features, and then you can take that data set, run data refined LLCs, and then find the part of your model that sort of cares about this feature. And then there's also some work that we want to do on investigating post-training. So these different refined LLCs might give us some insight, for example, into how deep or robust safety tuning really is. We might learn something from how the model changes in relation to safety tuning. And we might even be able to ultimately say something about the sort of relative like robustness or reliability of different safety tuning techniques. And of course, there's plenty more. So we have a lot more that we'd like to explore than we have, I guess, the capacity to work on. But if you have more ideas, we're always open to discussions. And if you want to work on anything, please talk to us or join our Discord or